All right. Hi, everyone. Thanks for joining before lunch. My name is Sean Kandel. I'm CTO, one of the founders of Trifacta. Today, I'm going to be talking about data lineage, and in particular, ways of visualizing and interacting with data lineage. So just real quickly, how many people are familiar with the concept of data lineage? OK, cool. That makes sense, I guess, if you're here. So real quickly, I'll do a little background on lineage, why we think it's important, and kind of motivate the problem. Then I'll get into some techniques that we've been developing at Trifacta. Quickly, I'll just a couple notes. One is that although I'm from Trifacta, nothing I'll show today really is the Trifacta product. We've kind of pulled everything out into standalone prototypes and visualizations that I'll show you. If you're kind of more curious about the product itself generally, or specifically how you can work with Lineage and Trifacta, grab me after the talk. And we also have a booth. I think it's 102 on the floor. The other thing I'll quickly say is that this talk builds off work I did or that I presented also at Strata San Jose earlier this year. So just in case anyone saw that talk, you'll see some new stuff in here as well, but some overlapping material in case you saw that talk. All right, great. So real quickly, for those not as familiar with the concept of data lineage, this is the definition if you look it up on Wikipedia. It says lineage is defined as a data lifecycle that includes the data's origins and where it moves over time. And the thing I really like about this definition is it stresses that lineage and kind of other topics related to data, such as data quality and governance and other stuff that kind of comes up in this context of data lineage, is not just about kind of where data starts and its origin, but also about all the things that happen to data throughout the life cycle, from kind of source data through all of the processing, transformation, cleaning, before it ultimately ends up in whatever kind of downstream report or analytics project. So it's important to understand not just kind of where data came from, but all of the things that happened in between the source and destination. And kind of generally, we found that lineage is actually critical in answering a ton of different questions that an organization might have about how its data is being used. So some examples, what are kind of the key data sets, the key table columns that are driving all of our KPIs? In kind of more secure settings, how is privacy-sensitive data being used? Are the right people accessing it? The people who do have access, how are they using that? Are they masking it in the right way? Is it kind of being treated properly, again, throughout that entire pipeline? And then kind of more generally, what are your calculations and transformations actually doing to the data? We found this is incredibly important as kind of data transformations become more complex. As the data is transformed in more and more ways, it can be incredibly complicated just to reason about how that data was produced. We've seen this in collaborative settings where you might have data that a team member prepared for you, and you want to understand what they've done. In other cases, in kind of highly regulated scenarios, we've seen that it's not enough to just kind of report on the results. You also need to report on how those results were obtained to show that they're being kind of calculated properly. So for all of these questions, generally what we're interested in is helping people reason about all of the steps in a data transformation, or what we would think of as kind of the lineage of the data. And for us at Trifacta, we're particularly interested in not just kind of capturing that lineage as you're kind of transforming your data or creating new calculations, but also helping you kind of visualize and then interact with that data so that you can quickly answer some of the questions that I was just mentioning. So before getting into kind of specifically what we've been working on, I wanted to talk a little bit about some of the related work in the industry, because this has been an important problem for decades now. There's been a ton of products out there that have addressed this in different ways. And then we think some of the stuff we're doing kind of fills an important gap. But again, so probably still by far today the most popular tool for working with data, transforming data, and so on is Microsoft Excel. So again, show of hands, I assume pretty much everyone here has used Microsoft Excel before. How many people in here knew about this track dependencies feature that I'm showing? Oh, actually, OK, a lot of people. I did not know about this until I started working on Lineage about a year or so ago. But pretty cool feature. If you select a given cell in your spreadsheet, you can look at kind of two types of dependencies. So the first one we would call kind of backwards facing lineage. The idea here is when you click a cell, you can see all of the other cells whose values went into the calculation to produce the cell you care about. And then kind of, in some ways, the opposite of that, forward lineage. Given a cell, what are all the other cells who depend on that value? So we would kind of classify this as cell or value level lineage. Gives you very kind of fine level granularity into an individual value, but not particularly useful if you're trying to reason about the entire logic of all of the steps that went into processing your data, or if you're kind of interested in an entire attribute or set of attributes. This kind of technique starts to break down a little bit, but very useful for kind of cell level dependencies. Kind of, at another extreme, if you're used to kind of, ETL tools or workflow products. So as an example here, we have Pentaho. They'll visualize the lineage typically by having kind of a graph where the nodes in the graph are kind of individual transformations. And then there's an edge between those nodes if there's kind of a dependency between those transformations. So here we can see we have kind of two independent transformation graphs that then get connected through this merge join, kind of on the bottom of the screen there. And then there's a couple extra steps of downstream processing after the join. So this has kind of the nice property that you can kind of see the entire graph, start reasoning about how the individual steps are related to each other, but you've kind of lost all the context now of the individual attributes, and you've lost the context of the data values. But certainly also a very popular choice for visualizing lineage. Kind of more recently, if you look at kind of popular tools in big data ecosystem like Cloudera Navigator, this is kind of tracing what we would think of as data set level lineage, or kind of very physical lineage, where you can see kind of the input source data, whether it's kind of a relational database or a file on disk. Some of the intermediate products that might get created, and then the output data, which again, could be a relational database or a file. So here, you've kind of abstracted away the logic of the transformations and instead are viewing kind of physical relationships between entire kind of physical entities on disk. And other products as well have kind of a similar approach. So this is Apache Atlas. And again, looking at kind of this, what we would classify as data set level lineage. So I think all of these techniques kind of have their pros and cons. One of the things we were focused on to kind of fill this gap is what we would think of as kind of attribute level lineage or column level data lineage. And the idea here is that we found that many of our customers are ultimately generating reports which are based on some metrics. And a lot of times the task is understanding for a given metric, what are the factors or features that led into that metric. If they've identified something that looks incorrect, they might want to know all of the other kind of input columns and all of the steps that led into that metric. Similarly, if they're kind of fixing something upstream as part of their logic, they want to know what are all the downstream effects of making that change. So that led us to really focus on what we would call kind of column level lineage. And to do that, we built a lineage visualization. And I'll kind of go through some of the inspiration for the design and a demo of how that visualization would work. So to kind of motivate this, I'm going to go through an example that I'll kind of use for the next part of the talk. It's kind of a very simplified example, but just to kind of motivate the problem here. at Trifacta, we have a free product that anyone can kind of download and use. And one of the things we're kind of asking is, how do we kind of get more adoption on the product? How do we encourage adoption? What are kind of the barriers to usage of the product? So as a simplified example of kind of studying this or kind of doing this analysis, we might look and see that are there people who have kind of a lot of friction just in the process of signing up? So as a first step, a user comes to our site and registers, downloads the product. We'll then measure the time between that initial registration and when they sign in. And then after they sign in, there's some time before they kind of upload and create their first data set in the free product. And we're going to want to kind of classify these gaps as normal or what we might say is kind of friction in that initial sign-up process. We might have a hypothesis that if there's a lot of friction in the sign-up process, this leads to kind of lower activity going forward or lower engagement. So kind of very simple hypothesis we might test. So to do this, really just 4 steps. We're going to start with a data transformation. So this is taking the raw data and transforming it to then produce the metrics I just described. We're going to then take the entire kind of transformation, a set of transformation steps, and try to identify dependencies at kind of the column or attribute level. Based on these dependencies, we'll build the dependency graph, and then finally we'll get into the kind of the interactive visualizations on top of that graph. So to give you an example of what this recipe might look like, just walk through this very quickly. In these first 3 lines here, we see we're going to split the data into rows, and then we're going to split it into a number of columns. So this is just kind of parsing out, say, a CSV file into rows and columns, and then we'll apply a header so you get your metadata in there. Finally, we might want to split out your email address into kind of the username and the domain. And we're going to do that so that we can delete any of the users who are maybe testing from Trifacta.com. So anyone from our company, we'll kind of throw them out of the analysis because we don't want it biasing the results. So we'll delete all those rows. And then if you recall from before, we were going to look at kind of 2 main metrics: how long it took before a user signed in after they registered. So that's the first column here we're going to create by computing the difference in time between the sign-in time and registration time. Similarly, we'll say a user is finally active once they've actually created a data set. So again, we'll look at the difference between the data set creation and the sign-in time. And then we'll just say, we'll kind of flag users as either having a delay in the funnel, if it took too long to sign in or too long to create a data set. If either of those metrics is high, we'll say there was some type of delay. And then finally, we'll kind of produce an aggregated report, which is how many users experienced a delay, and as a simplified measure of activity, how many jobs did they run on the platform going forward. And we can group those by either experiencing friction or not experiencing friction. So this is about 8 or 9 lines here. I'd say this is, again, kind of almost a very trivial transformation recipe. So I'll show you some of the techniques we'll use on a recipe of this size. In practice, we've seen customers who have recipes of dozens, hundreds, even kind of thousands of steps. So some of the techniques we'll want to scale, or all the techniques we'll want to scale to kind of that order of magnitude. And I'll talk a little bit about how we can do that. So we have our kind of transformations, or what we call a recipe. We're then going to analyze those transformations and identify dependencies. I won't say much about that here, except that we're going to go through each transformation and kind of parse out the dependencies. For us, we end up producing this kind of JSON file. Not that interesting, except potentially we found that there's actually a lot of other tools out there that are really good at managing metadata, for examining lineage, and so on. So to the extent possible, we kind of encourage all tools to kind of make this type of metadata externally accessible, either through APIs or other mechanisms, so that other kind of tools like cataloging tools or some of the governance tools I mentioned before, like Navigator and Atlas, can pick up that data. So just some examples of this, but again, kind of this very large ecosystem now of both kind of vendors and open source solutions for managing metadata, for cataloging metadata. So again, to the extent possible, making any metadata that tools are capturing interoperable with those systems, I think is an incredibly important thing to do. So once we have these transformations, we're then going to build up a dependency graph on top of all the individual dependencies. So the idea here is that for any given transformation, we can say, what are the dependencies that it produces? And then we're going to build up a graph that kind of tracks those dependencies throughout the entire recipe. So to give you a quick sense of how this works, to build a graph, we're just going to need some nodes and edges. So for us, a node is any kind of unique version of a table column. So the idea here is anytime a new attribute is created, that would create a new node, or if that attribute is changed in some way. So if we remove the quotes from a column, that would create a new table column. If we delete all the records where there's missing values in a column, that would in some sense change all of the columns, and we would create a new node for each of the columns in the table. And then we're going to make an edge between columns if during a single transformation step, there's some dependency between the input columns and those output columns. And for the purpose of this talk, we really focus on two types of dependencies. The first one we would call kind of direct or value dependencies. And the idea here is that when you produce a new attribute or metric, it might directly depend on values from other columns. So some quick examples here to kind of illustrate, if we were analyzing portfolio performance and wanted to look at the order size when we're buying and trading stocks, we would look at the price, and we would multiply that by the number of shares to get an order size. And we would say order size now kind of directly depends on the price and the shares. In this other example I talked about before, if we split kind of an email column into username and domain, we would say that those two attributes now directly depend on the email. And then in this last example, to kind of illustrate the two types of dependencies, if we were to say, look at total sales per location, we would say that that attribute, total sales, kind of directly depends on the values of sales, and only kind of indirectly depends on location. Because we're grouping on location, that will influence the final result. But in some sense, you could still calculate total sales if we removed location. But if we got rid of the sales column, there's no values to even sum up. So that's kind of the distinction we'll make. And to make this a little clearer again with condition dependencies, we're going to say kind of the values or the output are kind of modulated or indirectly affected by another column. So same example here, we would say total sales kind of indirectly depends on location. These next two examples, we're doing a deletion. So if we delete all the users from Trifacta.com or test.com, we would say now all of the columns indirectly depend on the domain. Because when we delete values from the domain, it's going to influence all the values in the columns downstream. And similarly, if you join two data sets together, now all of the output columns kind of indirectly depend on the join keys that went into that join. So you can see already here, especially in these last two examples, one of the reasons we make this distinction between kind of direct dependencies and indirect dependencies, or condition dependencies, is that in many cases you're going to have many, many more conditional dependencies. Anytime you delete some values, that's going to affect all of your columns. So we'll want quick ways to kind of filter those out when we're trying to visualize and interact with the lineage graph. So that kind of talks about building the underlying data structure. The last step will just be to then visualize the graph. So I wanted to talk about a few techniques we've seen in the past. So actually, let me pull this up in Excel here. So probably one of the more popular ways we've seen actually of visualizing this information. Let me blow this up. Is kind of an external spreadsheets, or maybe it's kind of more of a cataloging tool, but this kind of very manual process of listing out all of the attributes. So this is actually something we've seen as a very popular approach for doing this, where you might see some of the derived attributes, and we'll kind of list them out as derived attributes. So here's the metrics we saw before, the time before sign-in, maybe who created it, maybe a description of what that metric is supposed to kind of capture, and then maybe kind of a formula or a more kind of physical description of the logic that actually went in behind it. And what you'll notice here is that the derived attributes themselves might depend on other derived attributes. So if you want to get a sense of the relationships across these attributes, you kind of go through this process where you would read either the formula or the description, and then kind of back up through the spreadsheet and find the other steps or the other columns and kind of trace back very manually through a system like this. So hopefully we can make this process a little bit easier. Oops. So to do that, we're going to visualize this information in a kind of an interactive graph. So kind of the first approach that you might take is using kind of a directed graph and using just kind of a standard kind of layout algorithm. And I'll kind of walk through this initial approach, where it kind of breaks down, and then how it led us to the approach we finally settled on. So the idea here is, again, that each of the nodes in the graph is in a unique version of a table column. And then we're going to draw edges or lines between the nodes if there's a dependency, between steps. So as you kind of go from left to right across the graph, you can think of that as an individual transformation step. And then there'll be a line if during that transformation step some dependency is introduced. And we're going to have kind of solid lines for the value dependencies or the direct dependencies. We use dotted lines for the conditional dependencies. And when we started off by building this, kind of right away we found a few issues with this. The first is that because the layout is determined using some type of kind of just standard graph layout, it becomes really hard to understand attributes across transformations. The nodes become kind of placed based on the layout algorithm. So it really kind of hampers search through the graph to identify the nodes of interest, or in this case, the columns of interest that you're interested in for your analysis. And second, or kind of lastly, that when you have a lot of edges in this kind of layout, it can really produce a lot of clutter. So we wanted to solve these problems. There's a couple of approaches we took to do this. One is by using interactions to kind of filter down the graph and reduce clutter. And the other is to use a little bit more control over node placement and layout in the graph. So to get to that next approach, we took inspiration from kind of some other work in these types of visualizations. Both from kind of timeline and genealogy visualization. So this is a very early example. I think one of the first examples I'm aware of kind of a timeline visualization. So this is from the mid-1700s. And just a snippet here, but the idea is that you can kind of plot the lives of historical figures, when they're born and until when they die. And it helps you kind of very quickly ask a bunch of questions, such as, when did two people overlap in time? Was one person born before another person? And so on. So you can quickly kind of answer these questions and pack a whole bunch of information very densely into this this type of chart. More recently, it's kind of a now fairly famous visualization from XKCD. So on the top, we have Lord of the Rings. The idea is that you kind of draw these lifelines. And for every individual, you can kind of draw their lifeline throughout time. So again, going left to right. And the lifelines kind of come together as individuals in the story are near each other. And then they kind of diverge as those individuals go away from each other. And then similarly down below here for Star Wars. A little bit more recently, this is some work that came out of Stanford in 2010 with Jeff Hare's group, who's also one of my co-founders at Trifacta. And the idea here is that you have these lifelines indicating relationships between people. So lifelines kind of come together when people get married, and then they diverge when people get divorced. And then you can see these kind of drop lines indicating children that come out of a marriage, or in other cases, come out of wedlock. And you can quickly, again, start noticing a number of relationships and, importantly, how they change over time. So you can see when people get married, when they get divorced, were children born out of wedlock, were people married to multiple people at once. All of those types of questions become very easy to read off this type of visualization. The other kind of interesting thing that came out of this work was they actually evaluated these two types of visualizations. So the first one on the left is kind of the traditional directed graph using some type of force-directed layout. And they compared this to kind of more of a lifeline approach here on the right. And they looked at two types of questions. So they would have people answer kind of structural queries and then temporal queries. So the idea with the structural query is answering a question like, who were the parents of someone, or were two people ever married? And what they found was for both of these types of charts, you could answer those questions in about the same amount of time. But as soon as you layered in any kind of temporal question, so a question about how things change over time, the graph on the right became significantly faster to answer those questions. And a large part of that is that the node placement is consistent, and the lifelines have a bit more control, so it's much easier to kind of trace relationships across this graph. So based on that, we decided to apply very similar techniques here that we've seen kind of for human relationships, and instead just apply it to data attributes. So we call this kind of a data lifeline, or a data field or column lifeline. And the idea is that we're going to lay out our data into columns. So each column in the graph will represent a transformation. So we can see in kind of that top row the same recipe steps from before, where we first split our data into rows and columns, apply a header, split out the email, rename, delete, derive some attributes, and then finally produce our aggregated report. And then the rows are going to be data lifelines. So we can use these rows to kind of trace attributes and their dependencies. And we can see kind of the gaps in the lifeline indicate where changes occur or a new version is introduced. And importantly, kind of we found that this type of layout supports really fast kind of scanning and finding attributes, and also provides some context of the overall transformation or script. So we started kind of with that static graph, and as I mentioned before, the graph can get very cluttered as you have more transformations, more columns, more dependencies between columns and transformations. So we wanted to layer in some interactions so that you can quickly kind of hone in on just the attributes you care about, or just the transformations you care about, and still kind of get the dependency information for that subset. So I'll go into a demo before we get into that, just to give you a sense of some of the basic interactions. Here we've selected kind of a single attribute in the middle of the recipe. So this is that time before sign-in attribute I mentioned before. And we have kind of yellow lines going back, so tracing the backward lineage from before. We can see that time before sign-in directly depends on the registration time and the sign-in time. If you recall, we were kind of taking the difference between those two values to create the time before sign-in. And then those values themselves have dependencies going back as well. In particular, they both indirectly depend on domain. Remember, we were deleting all the domains from Trifacta.com, so that introduced kind of that indirect dependency across all the attributes in that deletion step. For the value dependencies, again, we'll use solid lines, and for the conditional dependencies, dotted lines. And then similarly going forward, we can see that time before sign-in is necessary and used to produce that delay in funnel attribute, which itself is then needed to produce the final report. So with that, I'll jump into a very quick demo. So again, this is the same visualization we saw before. We have kind of the header or the names of the columns going across. We have the recipe steps. And then we have individual attributes in the graph here. So I'll just go through some of the basic interactions and then show how we start scaling this up to larger data sets. So first, if we select a very simple attribute like username, we can see that username itself depends on the first half of the email. If we remember, this was splitting the email into kind of two component parts. In the email itself, this first part depends on the email attribute, which depends on kind of the raw data source. Going forward, we can see that the username that gets changed when we apply that deletion to delete everyone from Trifacta. And then already kind of interestingly, we can see one thing, which is this attribute is in fact never even used in the analysis. So you can already start getting some information about this data even with this kind of simple interaction here. If we zoom in on domain, we see kind of a similar backwards facing history, but perhaps more interestingly, we see that all of the columns downstream become dependent on domain, again, because of this indirect or kind of conditional dependency. So you can see here, it starts getting cluttered very quickly when you have these types of dependencies, so we'll want ways of dealing with this. So as an example of this, let's go back to the time before sign-in. Again, now we see that time before sign-in depends on a few attributes, which again themselves have kind of upstream dependencies. So we want ways of potentially interacting with this to kind of reduce some of the clutter so we can reason about just these attributes. So I'll show you a few interactions we've added into that. So the first is when we kind of control click this attribute, we can immediately just eliminate any of the indirect dependencies which were causing a lot of clutter before. So now we've reduced this graph only to the nodes that are directly influencing that node or directly depend on it. But we can take this one step further by also removing any transformation steps that aren't actually impacting these attributes by collapsing this selection. So this is kind of a simplified example with about 10 attributes and 10 transformations. But you can see how we've kind of reduced a bunch of that information very quickly down to just a few attributes that are actually impacted by this one. And then we can, of course, kind of reset the graph. Similarly, if we wanted to zoom in on kind of the downstream or the actual end result and see what are the columns that are actually impacting the final results or final analysis, we could start kind of shift selecting those columns and tracing back all their dependencies, or select the entire step and again collapse this. Now to zoom in on only those attributes which are impacting the final result. Let's move on to a couple other examples. So in this case, it's very common to have kind of multiple data sets coming together to produce a result. So here we see kind of a similar script from before, but then we load in an external data set and join those two data sets together. So if we look at kind of account ID here in the final result, we see that this account ID directly depends on the account ID from the original data set, but also now indirectly depends because of this join key relationship. And if we look at other attributes, we see similar things here where these attributes kind of directly depend on attributes from the original data set and now have two indirect dependencies back to the join keys in the two data sets that we joined together. Similarly, if we look at kind of a union relationship, as we union data sets together, in this case, 3 data sets together, we can see each of these attributes depends on multiple columns. And similarly, if we kind of go down to the end here, we can see how these columns ultimately depend on multiple columns from multiple sources. So all of those examples, I would say, are kind of working on toy scripts, I would say, only a few lines. So we wanted to see what happens when we start applying this to data sets with many more columns and many more attributes. So here's a data set with on the order of about, I think, maybe 60 or 70 steps. And you can see it starts becoming a little harder to track how these dependencies change over time. So what we wanted to do was introduce a few techniques to make this a little bit easier. So I'll walk through some of the small stuff we do there. So one thing you'll notice is as you kind of scroll left to right, on the far left there, we'll kind of replace attributes with the most recent version of the schema. So this is just to give you some context and kind of ground the relationships as you're scrolling across. And then the other thing you'll notice as we scroll across is that there's oftentimes, and we found this a lot, when you have really large recipes, there's often usually steps that kind of repeat, either individual steps or kind of multiple steps, kind of like macros where you'll kind of repeat the same sequences of transformations. So to deal with that, we've added in what we call kind of the overview feature. And the idea there is to look at the dependency graph, try to detect kind of recurring subgraphs within that structure and collapse them into kind of single nodes. So when you click this overview, you can see the graph kind of collapses, and now you have much fewer steps as those stages kind of come together, or those transforms come together. So it becomes, again, much easier to kind of reason about those steps. Lastly, I'll say one of the things we've noticed in these types of analysis is oftentimes you don't really care about all the individual steps, but you might just care about how the attributes changed across maybe the entire recipe or some large chunk of the script. So to deal with that, we have this compare steps feature that we've added in where you can select kind of multiple steps. In this case, maybe we'll start with where we initially define the metadata. If we go down to the end here, we can select kind of the last step here, and when we compare the steps, again, we'll collapse kind of all the logic, get rid of all the intermediate steps you might not care about, but rewire the graph so that we can still trace dependencies across attributes. So we can see this first name in the output depends on just these 4 or 5 columns in the input. And similarly, you can go down and kind of zoom in on just the attributes of interest across the data steps of interest. So I know short on time a bit. I wanted to talk a little bit about some of the kind of technical concerns when building a system like this. So I'll try to move quickly through these. The first is how to actually parse the dependencies so that we can actually build up this graph. I think the most important thing here that we found is that you can actually encapsulate all the dependencies by just implementing parsing for a very small primitive set of transformations. So in most transformation languages, whether it's SQL or MapReduce or variants of Spark, or for us in Trifacta, there's often only a small subset of primitives on which every other transformation is kind of built. So if you implement the dependency graph just for a small subset, you can then kind of compute the dependencies independent of the underlying engine. So this is important if you wanted to apply these same techniques to a different language outside of Trifacta. You can actually do that quite easily by just implementing the dependency parsing logic for usually about 10 to a dozen different types of transformations. And just to give you an example of how this works, if we look at some transformations, such as, say, a lookup, that can be implemented as the dependencies for a join, possibly with some post filtering. Pivoting can be done through a map side operation followed by an aggregate, and so on. So this allows you to build up these graphs very easily for any kind of language for processing data. One other thing I'll say, kind of all the interactions are built on top of what we kind of call lineage queries, which themselves are just a simple graph traversal. So we can just, when you select a node or want to filter the graph, we can just kind of zoom in on a node, follow its dependencies forwards or backwards, and rewire a graph based on any kind of filtering of the graph that we want to do. So we call this kind of filtering and collapsing. And what's nice here is that by just implementing kind of one technique, you can support all of the interactions that I showed before. So the idea here is that you take some predicate and you apply it to your nodes or your edges. So this could be you only want to keep conditional dependencies. It could be you only want nodes from a given transform or columns with a certain name. Then you just remove all the nodes or edges that don't match that predicate, and then we simply kind of do another graph traversal to rewire the remaining nodes. So if you start with an input graph here, we can apply a predicate, analyze the links, and then finally kind of collapse this into the output graph. I'm going to jump ahead a bit because I know I'm short on time. To the conclusion, next steps, and happy to talk more about this offline, is to apply this type of visualization. Very easily, you can apply this, as I mentioned before, to other types of transformation language. Once you have the graph, all the visualizations and interaction techniques are, in some sense, agnostic to the underlying language. You could also imagine applying these types of techniques to database query plans to understand how to optimize those better or where you might get slowdowns and so on. Finally, the other things we've been looking at is incorporating what we call profile data. So these could be summary statistics or important metrics. So instead of just looking at the attributes and how those change over time, by computing summary statistics throughout those transformation steps, you can instead also look at important metrics and how those change across those transformations, and another way to kind of view dependencies and how they affect important statistics or data quality issues of interest. And with that, I'd like to open up to any questions. And again, we're at booth 102 if you want any more information. Thank you. Sure. So we actually, we support pivoting and unpivoting. Those are both supported by this graph structure. In terms of actually, are you talking about defining the transformations or just visualizing the dependencies? So kind of at the logical level, I think the similar techniques that I showed here work. Oftentimes there you'll see a lot of other attributes disappear during pivoting because you're kind of aggregating up. So I think those techniques work. In terms of visualizing how the data changes, I think other techniques are kind of more appropriate there, less kind of related to the logical representation of the transformations.
My question is related to the arcs or the links.
Yep.
Usually, if it is a graph database or graph approach, it has attributes like the mid-step. My question is any option to display those attributes, like for example, which is the versioning from one step to the other, because maybe it is done in different versions. I see it's really strong appliance to documentation, in my case, to flow documentation.
Yep.
So do you have that kind of implementation? That you, you double click or you right click on the arc of this, and you get who did the transformation, what was the version, what it was used, who approved it, and all these things?
So yeah, I guess I didn't mention what we're doing in Trifacta as much, but within the product itself, there's a whole kind of audit history. And when you get into collaborative scenarios, you can see for a given transformation, who added it, when they added it, and you get kind of your own internal history as well as a history across the group of transformations.
But it would be linked to this way of displaying things? You have to go a different place, or it is integrated in the...
Oh, I see. So yeah, I think probably the best is if you stop by, we can give you a whole demo of how all those things work. Yeah.
Quite interesting.
All right. Great.
Any other questions? Maybe they
Okay. Great. Yeah. Thank you.